طيب شباب, let's continue with lecture 35, where we're gonna solve only one part of problem 614. So remember, we said one of the great benefits of using semi-batch reactor is to increase the selectivity in liquid phase reactions, and we also said if I'm using unsteady state operation for a non-batch reactor, our preferred variable will not be x, it will be either number of moles, molar flow rate, or concentration. Okay, so we're going to apply all of this in this lecture. طيب, so let's read the problem statement. The product D is to be produced through the reaction of A with B in an isothermal semi-batch reactor initially filled with one of the reactants while the other is continuously fed to the reactor. The following reactions take place. So A plus 2B gives you C plus D, and you have the rate law given. However, some of the product D reacts with one of the reactants, which is A, through this reaction to form C and E. Also, there's another side reaction which occurs, that is where C, one of the products, reacts with B, one of the reactants, to form D and F. So we're kind of lucky with getting D through this side reaction as well. طيب, additional information: constant density liquid phase reaction. We have the values for the rate constants are given, identified through chemistry, of course, and we have also few other parameters like epsilon naught. So this is a suggested molar volumetric flow rate given for the feed, 1 liter per minute. VI, so initially we should fill the reactor by 40 liter. This is another suggested value. VI is V initial. And we have the concentration of pure A and concentration of pure B are given as well. So what's required? Well, we need to determine which of the reactants should be initially charged and which should be continuously fed, and we should justify our choice. And we should also plot the species concentrations, conversion, overall selectivity, and overall yield as a function of time. And also the third question, what are the maximum CD and ND and when are they reached? And finally, we should inspect the CI profiles and discuss how CD max can be further increased. طيب, let's start with the first requirement. Determine which of the reactants should be initially charged and which should be continuously fed, and we should justify our choice. Okay, so what do you think, Shabab? How can we determine which reactant should be fed continuously and which one should be initially charged into the reactor? Basically, we are asking which species should have high concentration and which species should be maintained at low concentration, correct? Well, in order to answer this question, we need to look at the remember, selectivity, صح? The instantaneous selectivity. So SD, where D is a desired product. Let's see which one is the undesired product. Well, C cannot be undesired product, it shows up with D. F cannot be a desired product, it shows up with D as well. So the only guy who can be blamed is E. And we say we wish you did not show up, correct? So that is, we need to write SDE, which is obviously RD over RE, correct? RD over RE. Okay, so when we say RD, we mean the net rate of formation of D. That's what I want to increase, correct? Compared to RE, which I want to minimize. So let's look at RD. We know that D is involved in all the three reactions. So we write equals RD1 plus RD2 plus RD3, and the value of RD1 is given. The equation for RD1 is given. RD2, well, RD2 is related to RE2. How can we relate it? Well, very simple. We relate it through the stoichiometry. RD2 divided by minus 2 equals RE2 divided by plus 1, correct? So this will leave us with RD2 equaling minus 2 RE2. Tamam? Okay, what about RD3? Well, that's quite simple. Let's look at the third reaction. It simply shows that RD3 simply equals RF3. Okay, tamam, very good. Okay, so let's go and write the equation for RD. Right. So SD over E equals RD, which equals RD1, where RD1 is KD1 CA CB squared. And then we have RD2, which equals minus 2 times RE2. So that is 2 times RE2, which is KE2 CA times CD. What about RD3? We said RD3 equals RF3. And RF3 equals, well, I guess we need to erase this in order to be able to write the rest. So that is plus KF3 CB times CC squared. Right, this is divided over RE, and we know that RE, so E is involved only in reaction 2, right? So RE equals RE2, correct? Okay, what does RE equals then? It simply equals KE2 times CA times CD. Can we simplify? Yes, we can. So we have KD1 divided by KE2, and then we have CA cancels out with CA, so we have CB squared divided by CD minus 2 plus we have here CB times CC square over CA times CD. Tamam? Okay, so looking at this instantaneous selectivity, what do you notice with respect to CB and CA? Well, you notice that if CB was high, then the instantaneous selectivity will be high, and also if CA was low, then the instantaneous selectivity will be high as well. So you want to maintain a high concentration. You want to maintain high concentration of CB and a low concentration of CA. So how do you do this? How do you maintain high concentration of B and low concentration of A throughout the reaction? Well, simply by initially charging the reactor with B, with pure B actually. And so this will ensure that you have high concentration of B. And slowly but continuously adding A to the reactor. This will ensure you that you have low concentration of A. Tamam? And I hope so that this is clear. طيب. Let's now discuss the second part of the question. Plot the species concentrations, X overall selectivity and overall yield as a function of time. Okay, so if you want to plot the concentrations, obviously we'll need to solve the design equations, the mole balances. So let's start writing the mole balances. Let's first start writing the general mole balance. Tamam. So the mole balance says input, which is Fi naught, minus output, which is Fi, plus generation, that is Ri times dV from 0 to V throughout the whole reaction mixture. Volume equals dNi by dt. You would know that you don't have any of the species going up, so that's 0. And when it comes to Fi naught, simply it can be written as Ci naught times epsilon naught, and then plus Ri, integration of Ri dV, that is Ri V. Ri V equals dNi by dt. طيب. Okay, so do we need to rearrange? Well, we could rearrange, or we could just simply stick to this form. Okay, so let's now write equations for how many species? Well, we need to plot all the species concentrations, so we have to write design equation for all the species. We have A, B, C, D, E, and F. So we have 6 species, so we need to write 6 of these equations. Let's start with A. So for A we have Ca naught, right, where naught is for the entering, times epsilon naught plus Ra times V, and I know the V is function of time, equals dNa by dt. And obviously this is a differential equation. In order to solve it, we need a initial condition. So let's write the initial condition. At t equals to 0, Na equals Na I initial, which equals 0, because we decided that initially we don't have anything inside the reactor except for B, correct? Okay, so that's one equation. We need to probably frame it because we're going to use it. And also frame the initial conditions. Okay, let's write for B. Let's write for B. We have concentration. Do you have B in the feed? No, we don't have B in the feed. So we remain with RB times V equals dNB divided by dt. And again, at t equals to 0, NB equals NBI, which equals a value, correct? How do you calculate this value? Well, you need to calculate it by, NBI equals CBI, which is pure B, right, times VI, which was around 40 liters. Yeah, it was 40 liters. And CBI is 2 moles per liter, so 2 times 40 will be 80 moles. Okay, let's frame it. Okay, let's try one more thing, one more reactant, and let's do it for, let's say, C. Okay, you can do it for C, no problem. For C, we have RC times V equals dNc divided by dt, and at time equals to 0, NC equals NCI, which equals 0. because at time 0 we don't have anything in the reactor except for B. And again we're gonna frame this and this because we're gonna enter it into the software. And let's continue. Well, you can continue this at home. You write a mole balance for E, well, your D, E, and F. Tamam? Okay. What else? What else? Well, what else we need? Yep, we said in these design equations, V is variable. So how do you find an equation for V? Well, we use mass balance, correct? So the mass balance states that m dot n minus m dot out equals dm by dt. So the mass coming in basically is rho naught times epsilon naught. Do you have any mass leaving out? No, we don't. Equals dm, we can write it as d rho v, volume of the reactor, dt. And we say it's a constant density system, so rho equals rho naught equals constant, right? So rho naught epsilon naught, if rho is constant, goes outside the derivative, and then we can cancel them out because rho equals rho naught. Okay, tamam. Okay, what else? So we are left with the simple equation, differential equation, which is dv by dt equals epsilon naught, and we know that at t equals to 0, v equals vi, which equals 40 liter, correct? Equals 40 liter. Again, frame this equation and frame the initial conditions. We're going to need it. Right, what about x? Okay, so we have B is initially charged, so I believe that x should be written for B. So xB, what does xB equal? Well, x is related number of moles or molar flow rate. So in here for B it's a batch system, so it's NB initial minus NB divided by NB initial. Make sure that you don't write NB not, because not here refers to the feed, right? Okay, and we calculated what NBI was, tamam, and NB we have an equation for. Remember, dNB by dNB by dt, and so on. Okay, we also need to define the overall selectivity and overall yield. Okay, never mind. So before we go there, let's continue with our design algorithm. So we are done with writing the mole balances, the design equations, correct? And whenever we have a variable, we provide an equation for, and that's what we did with dv by dt to find an equation for v as a function of time. Right. What comes next? The second, of course, step is to write the rate laws, right? To write the rate laws, and we already have the rate laws here written and given. Tamam? So that's step number 2. Step number 3 is related to stoichiometry. What do we need in the stoichiometry? Well, first of all, we need to write all the rate of reactions, right? The net rate of reactions. For instance, we already wrote for D, right? We said RD equals RD1 plus RD2 plus RD3, right? Let's look at A. Okay, let's write for A. So RA equals R1, sorry, RA1, should write be consistent, RA1 plus RA2 plus RA3. and you can see that A is not involved in the third reaction, so this guy goes to 0. Okay, so we have RA1 and RA2. Tamam, and we'll need this equation, or maybe we should have framed it in red. Type. So that was for A, but we did not finish because we need an equation for RA1. How do we write an equation for RA1? Well, simply we write it as follows. RA1 divided by minus 1 equals RD1 divided by plus 1, right? Okay, so this will give us an equation for RA1. RA1 equals minus RD1. And then, of course, we'll need to frame this as well. What about RA2? Well, here we have RA2 divided by minus 3 equals RE2. Yeah, we have RE2. So it's RE2 divided by plus 1. So therefore, RA2, I don't know where we should write it. Well, maybe you allow me to erase this. Come on. And right now, RA2 equals minus 3 RE2. Come on, and then we frame it as well. Right, so now we are done with A, correct? Let's do the same but for B this time. Right, we are still in step number 3, which is utilizing stoichiometry, and we are continuing with writing the net rates and then finding the rates of each species through each reaction through stoichiometry. Okay, so we're done with A. Let's continue with B. Okay, so RB equals RB1 plus RB2 plus RB3. Let's look at B, and B is not involved through reaction 2, so this is 0. So I'm remaining with RB equals RB1 plus RB3. And what RB1 equals? Well, we can find it from the stoichiometry as RB1 divided by minus 2 equals RD1, because that's what we have, that's the rate law we have, divided by plus 1. Therefore, we can write RB1 equals minus 2 RD1, and we frame it because we're gonna enter it in the software. Okay, let's continue. RB3, yeah, we need RB3, and we know that RB3 divided by minus 1 equals RF3, which we have a rate law for, divided by plus 1. Therefore, RB3 equals minus RF3, and we frame it as well. Okay, let's not forget to frame this. And then we continue with RC, RD, and all the way. Right. Are we done with the stoichiometry? Well, not really. Let's look at the design equation. In the design equation, we have the right-hand side, which is dNi by dt. We have number of moles, correct? And the left-hand side, we have the reaction rate, which is expressed in terms of concentration, correct? So maybe we need to express the concentration in terms of number of moles. So that means we have to express, maybe it's better to do it in black. So we have to express Ca equals Na divided by V, and we know that V is function of time, correct? So this way, now the design equation can both be expressed in terms of number of moles, and we also write Cb equals Nb divided by V. Simply, we have to write Ci as Ni divided by V, and we write it for all the species. And then, of course, we need to frame all of these equations. Okay, so we're done with the stoichiometry. We let the combine and the evaluate to be done by the software. Okay, so evaluate. Let's evaluate the parameters first. We write all the parameters that we need, their values. If there's an equation we have to add, let's add it. We said for x, the equation was nbi minus nb divided by nbi, tamam, and for the overall selectivity, tilde, right? So selectivity is the comparison between the desired product and the undesired product. So in this case we have d over e, and this is n d minus n d naught, we don't have n d naught, divided by n e, tamam. And then we have y tilde, that is for d, this is how much nd is formed, correct, divided by how much how much b is consumed, that is nbi minus nb. This gives you how much b is consumed and went to the right product, which is d. Okay, we need to frame all of these guys, and again we need to make sure how to define the nbi. For instance, we said already nbi equals Cbi, which was the concentration of pure B, 2 mol per liter, multiplied by Vi, which was 40 liter. Okay, one more thing we need to be aware of, that this value equals to infinity at time 0, because at time 0 Nd is 0 and E is 0, so 0 over 0 is infinity. The software will be jammed, cannot really proceed with a solution, with a numerical solution. So that means you need to use an if statement. You say, well, this is the definition of tilde s if n is greater than 0. However, if n is else, yani if t is 0, then you give it any value that you don't care about, okay? Or simply you can add here very small value, tamam, and then this way it really doesn't have to be undefined at time equals to 0, okay? And the same thing goes to the yield. Okay, so after typing in all these framed equations and evaluating all the parameters, plugging in all the values of k's, of epsilon naught, of ca naught, and so on, we go ahead and solve. This is the solution. Now you can see all the concentration profiles for all the species. We have 6 of them. Tamam, let's concentrate on 4 of them. Okay, 4 of them. So you see that the concentration of B is continuously reducing because B is a reactant, right? And it was initially charged with an initial concentration of 2 molar, 2 molar, and then with time it's getting consumed. Let's look at concentration of A. You see the concentration of A is continuously increasing because we keep adding A, and A is a reactant. Is a reactant. However, it seems that the rate at which we are adding A is more than the rate at which A is being consumed. So let's say it again. The rate at which A is added the rate at which A is added is more than the rate at which A is consumed through reaction 1 and reaction 2. A is consumed through reaction 1 and 2. So it's being consumed. However, I'm adding the rate at which I'm adding A through epsilon naught is more than the rate at which it's being consumed. Therefore, the concentration of A continues to increase. Let's look at E. The same story with E here. E is only a product, so as the reaction progresses, its concentration increases. Let's look at D. Its concentration is increasing and it reaches a maximum value and then keeps decreasing. Why is that? Well, let's see. D is being formed through reaction 1 and reaction 3. At the same time, D is being consumed through reaction 2. So obviously, at the beginning of the reaction, at the beginning of the process, the rate at which D is being formed through reaction 1 and 3 is more than the rate at which D is being consumed through reaction 2. Why is that? Well, initially we have high concentration of B. Tamam. We have high concentration of B. Therefore, we have high rate of production of D, right? At the same time, we have low concentration of D, okay, and low concentration of A. Therefore, low rate of consumption of D through reaction 2. But as the reaction progresses, the concentration of D increases, the concentration of A increases, and therefore the rate at which D is consumed become appreciable. Tamam. At the same time, the concentration of B is reduced. Okay. Therefore, the rate of the first and the third reaction reduces as well. Therefore, we have the rate at which D is consumed through reaction 2 becomes more than the rate at which D is produced through reaction 1 and 3. And therefore, D continues decreasing. Okay, CD max. Well, you can see that CD max is around 0.377 molar at a time of around 21 minutes. Okay, let's look at number of moles. Well, you can look at number of moles by multiplying the CD by V. So ND equals CD times V. Tamam. And you can see that the maximum number of moles of N is 24, and that's around 28 minutes. 28 minutes. So maybe you do need to wait a bit more than 21 minutes, right? Okay, let's look at the volume. The volume is increasing from the beginning of the process to the end of the process. Let's look number of moles of D. Again, we say it's reached maximum around 28 minutes. Okay, what are the maximum CD and ND and when are they reached? We discussed that already. Let's inspect the CI profiles and discuss how CD max can be further increased. How can you increase CD now? Okay, let's go to this again. Well, if you want to increase CD, you need to increase the instantaneous selectivity. If you need to increase this instantaneous selectivity, remember, if you want to increase the instantaneous selectivity, you need to maintain a high concentration of B and low concentration of A. But as you can see here, the concentration of A is building up. So maybe you should slow down on the epsilon naught, right? So that the rate at which A is added is not higher than the rate at which A is consumed. So let's slow down. That's something we can do. Slow down on the concentration of, slow down the rate of addition of A. Of course, you can do other things, like for example adding B as well with A. Tamam, we can do that if you want. And maybe if you look at the spontaneous selectivity, you can suggest other things if possible. But of course, the easiest thing to do is to keep or to reduce the epsilon naught. But what happens if you reduce epsilon naught? Well, I'm sure the CD and ND max will both increase, but they will reach their maximum at a longer time. So you will not need around 38 minutes. No, you will need more. And if you wait more, that will affect negatively the number of batches you can run per day. So therefore, there is a optimization as well there. Okay, last thing. Recall that we said there often is a conflict between selectivity and conversion. So let's look at selectivity and conversion and yield. Okay, the green line, dotted line, is the XB. So you can see as time passes, conversion of B increases. Let's look at the selectivity. Here the selectivity was too large, so I divided the selectivity by 100 and plotted here. And as you said, at the initial time, selectivity is meaningless because of the tricks we use. Okay, but anyway, let's see if at maybe 5 minutes the selectivity is huge. However, it keeps decreasing as the reaction progresses. Tamam. And let's look at the yield. The yield starts as a value, increases a little bit, and then keeps decreasing. Remember, Shabab, we said there often is a conflict between selectivity and conversion. See, when we had large selectivity, we had small conversion. If we waited more to get higher conversion, we'll end up with lower selectivity. So there is a conflict because you want to make a lot of desired product B and at the same time minimize the undesired product U. So you can see the conflict there. So that means again there is an optimization in our operation. طيب, so we completed that problem. I'll leave you to play with it at home, but please remember to solve the suggested problem set number 8 and solve also the chapter 6 examples. Of course, here we did not really discuss the example of chapter 6 because they are simply based on the isothermal reactor design and also based on few equations related to stoichiometry and so on. Okay, and don't forget to play also the tic-tac-toe game. Thank you for listening, and we'll see you in the next lecture.